Dear students, will continue our discussion on PN junction in forward bias. We had already discussed this thing that in forward bias, in a forward biased diode, the minority carriers of P and N region, they will move away from the junction. Move away from the junction and will accumulate and store in the device and will accumulate and store in the device, and and therefore in a forward bias diode, the current is due to minority carriers. Minority carrier, the current due to minority carrier is zero. Okay? The current due to minority carrier is zero because these minority carriers, either from P side and N side, they will move away from the junction and they will get accumulated inside the diode. Therefore, they will not contribute to the current. They will not contribute to the current. Okay. Now see, the time taken to store the minority carriers, the time taken to store the minority carriers in the forward bias diode, it is referred as minority carrier storage time. Minority carrier storage time. Okay, so it is referred as minority carrier storage time. The forward current in a diode is diffusion current. Forward current is a diffusion current, and forward current is due to majority carriers only. Majority carriers only. Because these majority carriers, they'll be crossing the junction from higher concentration to lower concentration, and due to property called as diffusion, which is the movement of charge carriers from higher concentration to lower concentration, the current will be established. Hence, the forward current is mainly due to uh, diffusion phenomenon. Okay, so if you have a junction here, for example, this is a junction and this is depletion region. You have a P side here and N side on this side. Then we will have majority carriers of holes in P side. We have majority carriers of holes in P side, and then we have electrons on N side. We know that these majority carriers, they will be diffused, they will move from this region to this region because the whole concentration is high in the P region. whereas the hole concentration is low in N-type semiconductor. So once the built-in potential will be provided, then these holes will move from higher concentration to lower concentration. Therefore, uh, the current will be due to the diffusion. So current will be due to diffusion. Okay. So in this junction, the majority carriers of the majority carriers of P and N region on crossing the junction will become minority carriers, will become minority carriers. Now see, a hole was majority carrier in P side, but once it got transported or it moved towards the N region, then here it is a minority carrier. Okay? Minority carrier. A hole in P side is a majority carrier, and an electron in N side is a majority carrier. But once the electron will move to the P side region, it will become a minority carrier in the P region. Similarly, a hole will become a minority carrier in N region or in N-type semiconductor. So the majority carriers of P and N region on crossing the junction will become the minority carriers. And in the region upon crossing the junction, they are called as excess minority carriers. Okay, because initially they were majority carriers, but where they moved in a region, now after crossing the junction, they became their minority carriers, and there was a natural concentration, there was an intrinsic, or there was some basic concentration of these majority carriers. But upon movement of these majority carriers to other area, they became now excess majority carriers. Excess majority carriers. Okay, so we are basically adding some more minority carriers. So they became excess minority carriers, not majority. Excess minority carriers. So we can say then forward current is due to flow of excess minority carriers. Forward current is due to flow of excess minority carriers inside a PN junction. Okay, inside a PN junction. Moreover, in a forward biased PN junction or diode, a PN junction is also known as a diode. Okay, so the current is controlled by the flow of excess minority carriers crossing the junction. So we can say then this forward current, if we have a diode and the diode is forward biased, the current that will flow through the diode, it is known as forward current, I of F. We can say then in forward bias diode, the forward current or the current is controlled by the flow of excess minority carriers crossing the junction. That is how much excess minority carriers will cross the junction. Accordingly, the current will be established in the diode. Okay, accordingly, the current will be established in the diode. Okay, so that was all about how the current flows through the forward biased PN junction. Now, there is something known as cut-in voltage. Cut-in voltage, which is referred as V of gamma. V of gamma. V of gamma. It is also known as offset voltage. Okay, then referred as V. It is also known as knee voltage, it is referred as V of K, or it is also referred as threshold voltage. Threshold voltage V, or it is known as breakdown voltage. These are all different names of the same parameter. Okay, breakdown voltage V, or V breakdown VBR. Now, cut-in voltage is defined as the minimum forward voltage required so that a current will pass into the diode. Okay, so it is cut-in voltage is defined as the minimum forward voltage required so that a current will pass into the diode. We have already discussed it that inside a diode, when you connect P and N regions together, so this is P side and this is N type semiconductor, there is a junction, there is a depletion region which cannot be crossed by the majority carriers on P side and majority carriers on N side very easily. And we said that that region, or um, that barrier, is known as depletion region. And we know that the depletion region width is given by W, and holes cannot cross this depletion region very easily. And electrons, on another hand, on from right hand side, cannot cross this depletion region very easily. There is a barrier kind of thing. Okay, so you have to provide some kind of potential first initially to these holes or electrons, so that their potential, their energy will be raised and they can easily cross that junction barrier. Okay, we have already seen that in forward bias, the depletion region width gets smaller, it gets smaller, it gets decreased. Okay, so it gets decreased. So there is a requirement of a voltage, so that it will enable the charge carriers from both the sides to cross this barrier, to cross this depletion region. So the minimum amount of voltage that is required so that the current will pass, or so that the charge carriers will pass, so that the holes will pass from P to N and electrons will pass from N to P, the minimum voltage, minimum forward voltage that is required, uh, so as this thing to happen, is known as cut-in voltage. That is what is cut-in voltage. Okay, so when cut-in voltage is applied to a diode, current will flow, and since the diode is in forward bias, the current which will flow, it will be forward current, I of F, forward current. And this forward current will flow only when you apply certain cut-in voltage V of gamma, okay, V of gamma to the diode externally. Now, cut-in voltage, the value of cut-in voltage is different for, different diodes. If the diode is made up of germanium, for germanium diode, the value of cut-in voltage is from 0.1 to 0.5 volt. Typically, it is 0.3 volts, okay, or 0.2 volt. It is typical value is 0.2 volts. For silicon diode, silicon-based diode, the value of cut-in voltage is 0.6 volts to 0.9 volts, and typical value is 0.7 volts. 0.7 volts. Okay, so it means that you have to apply 0.7 volts externally to the diode, then only the forward current will flow. Then only the forward current will flow. Okay, then only the forward current will flow. Okay. Now, another condition, diode or PN junction in reverse bias. in reverse bias, or sometimes we say blocking bias on PN junction. Blocking bias. Sometimes we say back biasing on a PN junction. Now, a PN junction is said to be in reverse bias condition if we discussed it yesterday, if an N side or a lower potential will be applied on P side and a higher potential will be applied on N side. Okay. Now the current that will flow in the reverse bias situation. So you can see that we have a positive higher potential on N side and a lower potential on P side. Now the current that will flow in a reverse bias condition, it is I or it is I of S, saturation current. Okay. And we have already discussed that in forward bias, the width of depletion region decreases. But in reverse bias condition, width of depletion region, it increases. Okay, it increases. How does it increase? I'll explain it here. So you have, this is N type here, and this is P type here. And we know that this is a depletion region somewhere here in zero bias condition. So you have negative immobile ions from N side, P side, and positive immobile ions from N side. Okay, so you have positive and electron, positive and electron. So you have negative and hole, negative and holes. You have negative and holes. Now see, once a reverse bias will be applied, we are applying a positive uh, on N type or N side and a negative on P side. So a positive voltage is applied on N side and a negative voltage is applied on P side. Now once the positive voltage is applied on N type, the electron will get attracted towards this. Electron will be depleted off towards, the positive terminal of the battery. Similarly, the holes will be depleted. Holes will be attracted towards the minus terminal, negative terminal. Now see, we will have now an effective width will be now more. Okay, effective width will be now more. So this was a natural width that we had. It was W with zero biasing condition, but due to reverse bias, now the width of depletion region increased. Width of depletion region increased. So the voltage which is applied, it is V or it is V reverse bias, VRB. Okay, V or VRB. We can show this phenomenon using band diagram also. We can say that using band diagram, we can have, suppose with zero biasing condition, we had a built-in potential of VBI. VBI. Okay. Now, because of reverse bias, the depletion region increased. The depletion region increased. Now the depletion region is more wide and there is more potential is required for these charge carriers to cross the barrier because the barrier is now wider, it is now larger. So additional energy will be required. So due to VRB, the potential also increased. Okay, the depletion region also increased. And the effective potential to cross the junction will be also higher now. It will be now using blue color. And Vj is the total junction potential now. Vj is the total junction potential. It is total junction potential. Okay. So we can say then junction voltage, which is given by V of j, will be equal to sum of VBI, that is built-in potential, and reverse bias in magnitude. Okay, we can say then Vj will be equal to Vbi plus Vrb, and this is seen from the diagram also. Okay, so we can conclude the discussion that under reverse bias condition, under reverse bias condition, two things will happen. One is the width of the depletion region or depletion layer increases. Okay, width of depletion layer increases. The second thing is the barrier height also increases. Barrier height also increases. Okay, width of depletion region in reverse bias or depletion layer in reverse bias therefore is directly proportional to root of V of J, junction voltage. Okay, and we can say then width is directly proportional to root of VBI plus VRB. Why? Because of equation A. Because Vj is equal to VBI plus VRB. Okay, so we can say that width of depletion region is directly proportional to root of VBI plus VRB. So in a reverse bias diode, please note it down that current is only due to flow of minority carriers. Current is due to only the flow of minority carriers. Now see in this diode, on p side electrons will be minority carriers. Okay, somewhere here electrons will be minority carriers, and on n side holes will be minority carriers. The current is established only when these electrons will move towards n side and these holes will move towards p side. Then we can say that current flows inside the diode. But the charge carriers that will flow to the opposite side, they are already minority carriers now. Okay, we can then summarize this discussion that in a reverse bias diode, in a reverse bias diode, current is only due to flow of minority carriers. Okay, current is due to flow of minority carriers. Therefore, this current is known as the current is uh, denoted by I naught and is known as reverse current. Reverse current, and it flows from N to P, N side to P side. Okay, current flows from N side to P side because the direction of current is opposite to the direction of electronic current. So holes will move from N to P. Therefore, the direction of current will be from N to P. Okay, current will be N to P. And this I naught is also known as, it is known as leakage current, or it is also known as reverse saturation current, or it is known as minority carrier current. It is also known as thermally generated current. Thermally generated current. And this reverse saturation current or leakage current, it is different for different diodes. If the diode is made up of germanium diode, then the leakage current is in microamperes. And if the diode is made up of silicon, then the current is in nanoamperes. So the leakage current in germanium diode is more, and leakage current in silicon diode is less. Okay, you can summarize this that I naught of germanium diode, it is greater than I naught of silicon diode. Leakage current in germanium is high as compared to the leakage current in silicon diode. And we should note it down that I naught, that is the leakage current, is independent of applied reverse voltage. It does not depend on how much reverse voltage is applied, okay? Because this current is saturation current. That is, this current is saturated with respect to applied voltage. Forward current highly depends on applied voltage, but reverse current does not depend on the applied voltage. It is independent of applied voltage. However, I naught is highly sensitive to temperature. I naught is highly sensitive to temperature. I naught is highly sensitive to temperature. For uh, for 1 degree centigrade, I naught approximately increases by 7% for both silicon and germanium. For 1 degree centigrade, I naught approximately approximately increases by 7% for both germanium and silicon based diodes. Okay, and I naught generally doubles for every 10 degrees centigrade in temperature. So if we have certain leakage current I naught at certain temperature T1, then you change the temperature, I naught will also change, and we can calculate what is the I naught at another temperature. So I naught at temperature T2 is given by I naught at temperature T1 into 2 to the power T2 minus T1 divided by 10. Divided by 10. This is how the leakage current is dependent on this temperature. Okay, on temperature. This is how it is dependent on temperature. Now see, in a reverse bias diode, majority carriers of P and N region will be moving away from the junction. It will be moving away from the junction, okay? And they will accumulate and will be stored in the device. Uh, in the device, see, I'll draw the junction diode here. If we have a PN junction like this, and we know that this is the width of depletion region, and we know that width of depletion region will be higher, it will be larger, okay? And we are applying a reverse bias. This is P type here, this is N type semiconductor on this side. We are applying a reverse bias, that means a positive voltage here and a negative voltage here, or a higher potential here and a lower potential on P side, okay? And what is the voltage that is applied? V or V reverse bias. V reverse bias. We know that because of this, the holes are majority carriers here. The holes are majority carriers. They'll be moving towards the N side, okay, towards the negative voltage applied. So they will move away from the junction. Similarly, we had electrons here. They will also move away from the junction. Now, these charge carriers, holes in P type are majority carrier, and electrons in N type, they are majority carriers. So they are here majority carriers of N. These are majority carriers of P. Okay, and we can note that these majority carriers, they are moving away from the junction. Okay, we can then summarize this. We can write down this. In a reverse bias diode, majority carriers move away from the junction. Away from the junction. And therefore they will accumulate and will be stored in the device, and therefore in reverse bias diode, majority carrier current is zero. Therefore in reverse bias diode we can say that the current, contribution of current, the current due to majority carriers is zero. We can say that the contribution of current due to majority carriers will be zero. The current through the device is only when a charge carrier uh, crosses the junction. When the charge carrier crosses a junction. Since these majority carriers, they are already moving away from the junction, Therefore, they will not contribute to any current. Hence, we can say that in a reverse bias diode, the contribution of current due to majority carriers, it is zero. So majority carriers do not contribute to current in reverse bias diode. Since majority carriers are blocked in crossing the junction, reverse bias is also known as blocking bias. Okay, therefore that is why I said that it is known as blocking bias. So reverse bias is also known as blocking bias because the majority carriers are blocked in crossing the junction. They are not allowed to cross the junction. Okay. In other words, the holes from N side, and electrons from P side, they will cross the junction. Okay. So if we have a PN junction now, I'll draw it again. This is PN junction and this is width of depletion region. And we know this is P-type semiconductor, N-type semiconductor. And we are applying a reverse bias. Okay, we are applying a reverse bias. A higher potential on N side and a lower potential on P side. Now we can say that on N side, a hole is a minority carrier. It will cross the junction and move towards P-type region. Similarly, an electron is a minority carrier on P side and it will cross towards N side. So basically the current that flows inside uh, a reverse bias diode, it is because of minority carriers only. It is because of minority carriers only. Okay, so this is the flow of electron. But the conventional current direction will be like this. Conventional current direction will be opposite to the direction of flow of electrons. Opposite to the flow of electrons. Okay. We can say then the reverse current here, reverse current is a drift current. Why it is a drift current? Despite of having a higher, wider depletion region, it is under the influence of external electric field, the minority carrier it is forced to cross the junction, because we know that in a wider depletion region on N side, we have a positive immobile charge, Similarly, we have a negative immobile charge on P side, okay, negative immobile charge on P side. Despite of such large barrier, due to influence under the influence of external electric field, these minority carriers are forced to cross the junction. So they are drifted across the junction. So reverse current is a drift current. Okay, reverse current is a drift current. And we should know that reverse current, please note it down, is due to minority carriers. Minority carriers. And these minority carriers will be crossing the junction from lower concentration to higher concentration. Lower concentration to higher concentration. Therefore, the reverse current is a drift current. Okay. Therefore, reverse current is a drift current. Is a drift current. Okay. It's a drift current. Okay. Width of depletion region. Width of depletion region in reverse bias diode. Width of depletion region in reverse bias diode. We know that in a reverse bias PN junction, the width of depletion region is given by W, and it is generally equal to twice epsilon by Q. I think I have derived it in previous lecture somewhere. 1 by NA plus 1 divided by ND, then voltage, input voltage. What is the voltage which is applied during the reverse bias? It is V naught or VBI plus VRB, or I can say VBI is VD. Okay, assuming that VD is equal to VBI, assuming that this is equal to this thing. So the width which will be measured by this mathematical formula, it will be in meters. It will be in meters. Or we can say that width is equal to twice epsilon by Q 1 by NA plus 1 by ND into V of J, because Vj is equal to Vbi plus Vd, and this will be also in meters. It will be also in meters. It will be also in meters. Okay. Now this is the width of the depletion region. Now equation for current I in reverse bias diode. In reverse bias diode. So what is the equation, or what is the relationship of current in a reverse bias diode? The current in reverse bias diode will be opposite, and it is given as minus times I of S into e to the power minus V divided by neta Vt minus 1. So this is the Shockley equation that we have already defined in forward bias also, but here we have a minus sign because the current will be opposite to the forward bias. Now here, if we see that I will be equal to minus I of S e to the power minus V neta Vt plus I of S. For germanium diode, for example, if we assume that we have a germanium based diode, and we assume that neta, for germanium based diode, neta is equal to 1, and we assume that Vt is equal to 26 millivolts. 26 millivolts. And we assume that V is equal to the voltage applied, that is the reverse voltage. V is equal to 5 volts. Okay, V is equal to 5 volts. And if we assume that I of S is equal to 10 to the power minus 6 amperes, then we can calculate that I will be equal to 10 to the power minus 6 e to the power minus 5 divided by 26 into 10 to the power minus 3. Okay, 10 to the power minus 3, which will be equal to 10 to the power minus 6 e to the power minus 5000 divided by 26. Okay, So the value will be something like 3.6 into 10 to the power minus 90. That is, the leakage current will be very small. Okay, it will be very small. So hence, current in reverse bias is very negligible. It is very small. Okay, it is very small. We can say that I is nearly equal to I of S, because we will have two parts. One is this part and another is this part. And yellow one will be 0. Yellow one will be 0. Okay, nearly 0. So we can say that the current in the reverse saturation, in reverse bias diode, is nearly equal to I of S. Okay, it is equal to I of S, and which is very small, of order of 10 to the power minus 6 amperes. That is in microamperes. It is in microamperes. Second topic, next we move to VI characteristics of a diode. Characteristics of diode. VI characteristics are known as voltage current characteristics. Voltage current characteristics of a diode. Here in VI characteristics, the first parameter, that is the voltage, it is plotted on x-axis. So V is plotted along x-axis, and the second parameter, that is y, that is I, it is plotted on the y-axis. It is plotted on the y-axis. So if we have a diode, for example, and we know that what is VI characteristics. First of all, VI characteristics, it is a plot between voltage across the diode and the current flowing through the diode. Okay, we know that when we apply certain voltage to diode, certain current will flow. Now the voltage can be applied in such a way that it can either lead to forward bias situation, or it can lead to reverse bias situation. Okay, forward and reverse bias. Voltage can be applied in such a way, it can be either forward bias situation, forward bias condition, or it can be reverse bias condition. In forward bias, the diode voltage will be Vd, for example, okay, and the current will be forward current I of F. In reverse bias, the diode voltage will be, for example, V of D, but in reverse bias, the current will be I of S, because reverse saturation current, okay, that is shown somewhere here, reverse saturation current. Therefore, for example, if we consider we have a diode, let us consider we are in forward bias. Okay, case 1, forward bias situation. So the voltage across the diode in forward bias, we know that a higher potential is applied on P side and a lower potential is applied on N side. And the voltage across the diode is VD. The voltage across the diode is VD, and the current through the diode is I of F. Okay, it is I of F. It is I of F. So current through the diode is I of F. So VI characteristics which are plotted for forward bias, they are known as forward characteristics. Forward characteristics. And forward characteristics of diode, it is plotted with I of F versus V of D, because in forward bias the current is I of F and voltage across the diode is VD. It is VD. It is VD. So we'll plot these currents, okay, and voltage, this current and voltage. This is how we draw the forward characteristics of diode. We know that in forward characteristics, So I said that uh, current is shown, that is I is shown on y-axis and voltage is shown on x-axis. Okay, this is in volts. We know that initially when you apply a forward bias up to knee voltage or up to built-in potential, the current will not flow because there is a barrier. Okay, so there is a barrier, so initially the current will be very small. But after, for example, after knee voltage, that is V of gamma, or cut-in voltage, after cut-in voltage or knee voltage, the current will start increasing because the diode is in forward bias and more current will flow. Because I said in forward bias, in order to establish a current inside a diode, a minimum voltage has to be applied that is equal to cut-in voltage, so that these charge carriers will cross the depletion region. So this region is basically from this point to this point. So depletion region is not crossed. Depletion region is not crossed. That is why the current will be very small. The current will be very small. But once the cut-in voltage has been achieved by the charge carriers, there will be large current. The current will flow now, uh, you know, exponentially. Okay, the current will flow exponentially. The current will flow exponentially. I'll draw it here because we know that I of f. Okay, we know that I of f, or I, it is equal to I of s into e to the power Vd by neta Vt. Okay, so we know that the current is approximated as exponential variation in the diode. The current is exponentially varying in the diode. That is why this curve or this line is exponential in nature. Okay, that is why it is in exponential nature. But one thing you have to understand, that at certain point we need the current will start flowing. Before that, the current will not be there inside the diode. The current will not be there because the depletion region has not been crossed. Okay, depletion region has not been crossed. And when the diode is reverse biased, the reverse voltage must be always less than breakdown voltage. What is breakdown voltage? Breakdown voltage is when the diode gets damaged. When the diode gets damaged. So that was the forward bias. First of all, let us now go to reverse bias. Case second, reverse bias condition. In reverse bias condition, you know that the VI characteristics will be like this. You have somewhere VBI or V gamma, and this is I said that in VI characteristics, V is on x-axis and I is on y-axis. So I, this is basically I diode, and this is voltage VD, voltage across the diode. Now in reverse bias situation, we know that reverse in reverse bias situation, we know that in reverse bias condition, on P side, you apply a higher potential, that is negative. On N side, you apply a positive potential. That means the polarity will be reversed. Okay, polarity will be reversed. Even the direction of current will be opposite now. Okay, in a reverse bias condition, what does happen? Now we have a PN junction diode, and we know this is P side and this is N side. We apply a negative voltage here and we apply a positive voltage here. Now the current flows from N to P. Current flows from N to P, and we know that this current is equal to I of S. Current flows from N to P. In forward bias, current used to flow from P to N, P to N. Okay, like in reverse bias, it will be now opposite. So direction of current will be opposite, and the polarity will be also opposite. Polarity will be also opposite. So the current, when you apply an opposite polarity, that means this is the polarity of of voltage that you will apply, and the current will be plotted on this axis. Okay, so this axis or this quadrant will be used now to plot. Okay, all right. So the current will be very small because in reverse bias we know current is very small. Current is very small, but at certain point, at a very large reverse bias, there will be a point which is known as V breakdown, when the junction will be damaged and current may increase, you know, linearly, or you know, the junction will be permanently damaged. Then it may, behave as a conducting one, or it may not behave. But one thing you have to understand, that current will be very small in the reverse bias condition. And we have to ensure that when a diode is reverse biased, it is reverse biased, the reverse voltage, the reverse voltage must be less than breakdown voltage. Breakdown voltage, because at after breakdown voltage the diode gets damaged. Breakdown voltage of diode, otherwise the diode will be destroyed. Otherwise diode will be destroyed. It will be destroyed. Okay. So we can say then VI characteristics are like this. If we talk about forward characteristics only, this is I and V. For the forward characteristics of diode, this is how it looks like. So this plot is basically I versus, or V versus I. V versus I. And we know that I increases exponentially. I increases exponentially. But if we plot log E, natural log E, if we plot log of E of I of F versus V of D curve, okay, then then the curve represents a straight line. So this is how it will be. It is a straight line then. Okay, so this will be V of Ni or V of gamma. This will be VD, and this will be I. It will represent straight line, because you are basically taking, log of some exponential quantity. Some exponential quantity. Okay, natural log of some exponential quantity. So this will be cancelled out. That is why it will be a straight line. It will be a straight line. So sometimes there it is mentioned that draw the IV characteristics. VI characteristics, in VI characteristics, V is first term is plotted on X and second is plotted on Y. In IV characteristics, this is plotted on X axis and V is plotted on Y axis. Then the graph will be something like this. It will be something like this. So you will have somewhere V of gamma, and you have voltage here, and this is current on this axis. This is current on this axis. Okay. And I talked something about breakdown voltage. Breakdown voltage. I said the breakdown voltage is the voltage while the diode will be damaged. Breakdown voltage. Breakdown voltage, which is denoted by VBR or B of V. VBR or B of V. Breakdown voltage VBR or P of V. Now, breakdown voltage, it is a manufacturer's specification. It is a manufacturer's specification. That means breakdown voltage, it varies from device to device. Breakdown voltage can be one value for one diode, and it can have another value for another diode. Okay. In general, we say that in any type of PN junction, breakdown voltage VBR, it is directly proportional, or it is inversely proportional to doping. So if you have a very high doping, breakdown voltage will be very small, because it will be damaged very easily. If you have very small doping, then the breakdown voltage will be very high. So for heavily doped PN junctions, VBR is always small. Please note it down that for heavily doped, VBR is very small. Okay. So diode, and please note it down that from VI characteristics, we can see that diode is, first of all, I'll go here. Okay. First of all, diode is a non-linear device. Okay. Diode is a non-linear. It varies exponentially. It is a non-linear device. Second thing, it is a unidirectional device. It is a unidirectional device. Okay, it is a unidirectional device because in forward bias the diode conducts, and in reverse bias diode does not conduct. Therefore, diode conducts in only one direction, that is in forward direction, in forward bias situation. That is why we say that diode is a unidirectional device. Okay, unidirectional device. So we can note it down then. Please note it down that diode is a nonlinear device. It is also active device. It is also active device and also a unidirectional device. It is also a unidirectional device. It is also a unidirectional device. Okay. And this takes us to different topic, which is known as diode resistance. Diode resistance. We know that when a diode will conduct some current, therefore, in forward direction, it conducts some current, and in reverse direction, in reverse bias situation, it does not conduct any current. Therefore, there will be some kind of electronic parameter or some measure of opposition to the flow of these charge carriers, which will be measured by its resistance. Okay, that is what is known as diode resistance. So diode resistance has two different values. In forward bias case, you have one value of the resistance for the diode, and in reverse bias, you have another value of the resistance. In forward bias situation, in forward bias case, the resistance is known as forward resistance. It is known as forward resistance. And we know that since the diode in forward bias conducts very easily, therefore the resistance in forward bias is very small. It is 10 ohm to 100 ohm. 10 ohm to 100 ohm. And we also know that in reverse bias condition, the diode does not carry current. It does not conduct in reverse bias. Okay, therefore the resistance which is offered in reverse bias, it is known as reverse resistance. And reverse resistance is denoted by R of R. Its value is greater than 1 mega ohm. So the resistance in reverse bias is very high. It is very high. Okay, resistance in reverse bias is very high. Now in forward bias, the resistance a diode could conduct because of two situations. Either only DC currents and voltages are applied, or AC currents and AC voltages are applied to the diode. In both the cases, it can conduct. If only DC, if only DC current is applied, if only DC current or DC voltage is applied, then the resistance which is offered by the diode is DC resistance. Okay, or it is also known as static resistance. If If AC voltages and currents are applied, then the resistance which is offered, it is known as AC resistance or dynamic resistance. Okay. AC resistance or dynamic resistance is represented by small r, which means change in the voltage, because alternating current AC is a variable voltage or variable current. Change in the voltage divided by change in the current, and the units will be ohms. Okay, units will be ohms. Units will be ohms. So I can say then the resistance of a diode when an AC signal is not applied is known as DC resistance or static resistance. And DC resistance or static resistance is referred as R of F. Okay, R of F means forward resistance, which is equal to forward voltage applied divided by forward current, V dash divided by I dash. And it will be also measured in ohms. It will be also measured in ohms. So at any point, we can measure this forward resistance or static resistance of a diode from the VI characteristics. If this is the VI characteristics of diode, you have I on y-axis, V on x-axis. You know that up to cut-in voltage, there will be no conduction, but after that, the current will exponentially increase. Okay, after that, the current will exponentially increase. Suppose we want to calculate here the value of static resistance, then we will find the corresponding value of current and corresponding value of voltage. So the value will be V dash and current will be I dash. Therefore here R of F will be equal to V dash divided by I dash. So the resistance of diode when signal is applied, when signal AC signal is not applied, it is known as DC resistance. And the value of DC resistance can be different, from different point at different points of this curve. It does not vary, although too much. But the resistance of a diode, the resistance of a diode when signal is applied, signal means AC signal is applied, is known as AC or dynamic AC or dynamic resistance. And we should note it down that DC resistance is greater than AC resistance. The value of static resistance is quite significant as compared to the value of dynamic resistance. Okay, or I can say that static resistance is much greater than dynamic resistance. Dynamic resistance, okay, is greater than dynamic resistance. And how is dynamic resistance calculated? Dynamic resistance. Dynamic resistance of a diode, it is given by R. Okay, R is equal to neta Vt divided by I of f, because this is all forward resistance of a diode in forward bias. Now see, at room temperature, if it is given that, suppose I of f, okay, for example, I of f, suppose I of f is equal to 26 milliamperes, and we know that for germanium based diode, what will be I of f, what will be r will be equal to, for germanium, neta is equal to 1, it will be 1 into Vt is 26 millivolts divided by I of f, we are assuming it is 26 milliamperes, then R will be equal to 1 ohm. Okay, at room temperature, R will be equal to 1 ohm for germanium. And for case of silicon, we know that neta is equal to 2, then R will be 2 into 26 millivolts divided by 26 milliamperes, which will be equal to 2 ohm. So for case of silicon, R will be equal to 2 ohm, which is for silicon. Okay, for case of silicon, it is 2 ohm. Hence, the dynamic resistance is more in silicon diode when compared to germanium diode. We can say that, hence, the dynamic resistance is more in silicon diode when compared to germanium diode. Okay, in general, this dynamic resistance is given as neta Vt by I of f, which is equal to neta Boltzmann's constant T Qi of f ohms. Okay, if we know dynamic resistance, we can then calculate dynamic conductance also of the diode. Dynamic conductance, which is represented by G. Dynamic conductance G is 1 by dynamic resistance, and its units will be ohm inverse, mho, or Siemens. Okay, or Siemens. Okay, and we can write then G is equal to I of f divided by neta Vt, ohm inverse, Okay, or we can say that conductance is directly proportional to I of f. Conductance is directly proportional to I of f. Or the general formula could be G is equal to Q I of f divided by neta Boltzmann's constant Kt, which will be in Siemens or ohm inverse. Okay. Now, based on this discussion, I'll draw the equivalent circuit of the diode. Okay, equivalent circuit of diode. Now, equivalent circuit of diode, when the diode is in forward bias. Okay, case 1, forward bias. Forward bias. In forward bias situation, uh, a higher potential is applied on P side and a lower potential is applied on N side. Then the diode, the equivalent circuit of the diode will be, a resistor, which is the forward resistance, R of F, in series with a voltage source, which is V of gamma, which is the knee voltage. Because you know that in order uh, to establish a current inside the diode, we have to apply minimum potential. Okay, this is the minimum potential. So I'll write down, in order to establish a current in a diode, a minimum potential, which is V of gamma, is required to be applied across the diode. It is required to be applied across the diode. And if this is anode and this is cathode, then anode will be on this side and cathode will be on this side in the equivalent circuit. So generally, if we know that forward resistance of diode is very small, if R of F is not given, sometimes it is not given, okay, then we can approximate R of F nearly equal to 0, or we can neglect R of F, neglect R of F if it is not given, okay. So if it is not given, then approximate circuit equivalent representation. If R of F not given, then diode will be approximated like this. It will be approximated like this. So this is anode and this is cathode. This is anode and this is cathode. Okay. Now, case second, when the diode is reverse bias. When diode is reverse bias. When diode is reverse bias, then we know that a higher potential is applied on N side and a lower potential is applied on anode. Okay. Then in that case, current will not flow, and we know that the diode will be approximated with reverse resistance R of R. Okay. Reverse resistance, which is very large, of order of mega ohms. Okay. And its typical value is greater or equal to 1 mega ohm. 1 mega ohm. I'll stop here. I'll continue the discussion in the next lecture. Thank you.